Okay, welcome to the seminar series in the new semester. Today, we are very happy to have Sahand Seifnashri as our first speaker. Sahand is at the Institute of Advanced Study, Princeton. Uh, Sahand is an excellent expert in quantum field theory and in particular its applications to condensed matter systems. I would characterize Sahan's work as being both creative and also systematic and solid. I benefited a lot from reading multiple of Sahan's papers before. Today, he's telling us about the lattice realizations of chiral gauge theory, which can be put in a broader theme of whether we may live in the matrix. And there are a lot of recent progress in this direction. Sahan, please go ahead.
Okay. Hello, everyone. Thank you very much. Thank you, Legion, for the very nice introduction. It's the nicest introduction I got, ever got. And thanks for attending my talks. Uh, okay. So yeah, today I will talk about this work. So exactly solvable chiral gauge theories on the lattice. It's mostly based on this paper from January that I put on archive and another work in progress, which hopefully will appear very soon on the archive in collaboration with Yichul Choi, postdoc at IES, Nati Seiberg, and Wucheng Zhang, a great graduate student at Princeton. And I should say that please feel free to interrupt me at any time if something was not clear. So it would be great if you could just ask question. So the talk would be more interactive. Okay, so let me start. Okay, so a general motivation for this talk is the big goal question. So the big question that we have in mind is to how to find a lattice formulation of standard models. So up to now, we don't know of any non-perturbative formulation of the standard model, and we would like to have one such non-perturbative definition of standard model. But this problem is difficult. We don't know how to do it because, for instance, it's very hard to put chiral fermions on the lattice, and standard model has chiral fermions. Why is it difficult to put chiral fermions on the lattice? One reason is because of the famous Nielsen-Ninomiya theorem that I try to very briefly review for those who are not familiar with it. Another reason that why it's difficult to put chiral fermions on the lattice is anomalies of chiral fermions, and realizing anomalies on the lattice, it's difficult. But even though it's difficult, this obstacle makes it difficult but not impossible to find a regularization of the standard model. And the reason being that the standard model at the end of the day is anomaly free. So it's free of any gauge anomalies. So there is some magical anomaly cancellation in the standard model. And because the standard model is anomaly free, there is no rigorous no-go theorem that tells us that it's impossible to put the standard model on the lattice. I mean, if you take individual chiral fermions, they might carry some anomaly. But if there is anomaly cancellation, there is really no non-perturbative no-go theorem why this is impossible. So one goal that we want to define in this talk, so that we go towards the big goal of putting standard model on the lattice, is to find a lattice realization of anomaly-free theories. So in particular, we want to find anomaly-free chiral gauge theories. So anomaly-free chiral lattice gauge theories. So that's a big goal. And in this talk, we're going to address this problem in 1+1 dimension for the case of abelian gauge theories, when the gauge group is just U1. So that's the goal of the talk. And
Question? Yeah,
yes, please.
please finish what you want to say.
No, go ahead.
Oh, okay. I guess California is not the only challenge to put the standard model on the lattice, right? Can you summarize what you think as the complete set of challenges?
So maybe in a few slides, I will explain some strategy of how I'm going to put it on the lattice and some difficulties. Maybe at that point you could ask again if what I said was not enough.
Okay, okay.
Yeah, I'm going to go a little bit more detail to it why it's difficult. Okay, so as I said, we're going to solve this problem in 1+1 dimension for abelian gauge theories. And I should say that this work is also closely related to this nice work, which was done in Euclidean language. Our model is different because it's exactly solvables and we solve it exactly. I believe their model should be also exactly solvables, but anyway, they didn't solve it. So that's one difference from this nice work. Another closely related work is this nice paper by Ryan Thorngen, John Perskill, and Lukasz Witkowski. And the difference, and our model is a little bit different. I believe our model has a more concrete Hamiltonian, that we have actually solved the model and found the spectrum, which would be in this new paper. That's the differences between these related works. So let's jump in and get a little bit more precise. So let me just start from the terminology. So let me say, what do I mean by chiral gauge theory? So just to set the terminology. So in a chiral gauge theory, the way I define it is that chiral gauge theory is a theory where the left moving and right moving fermions transform differently under the gauge group. Okay. So because of that, the Lagrangian breaks reflection symmetry and is chiral in that sense, that it doesn't have a reflection or parity symmetry. So lattice regularization of such theories requires the realization of exact chiral symmetries of individual chiral fermions on the lattice. Because, if the left and right moving fermions transform differently under gauge group, so you want to first realize the left moving symmetries and right moving chiral symmetries exactly on the lattice, and then you gauge some anomaly-free combination of them. So difficulty of putting chiral fermions on the lattice is in the difficulty of realization of exact chiral symmetry. And that's going to be one of the most important obstacle that in this talk I'm going to try to answer. I'm going to also answer other questions, but that's one of the big problems. Like in 4-dimension, if you want to put a standard model on the lattice, you could put just free fermions on the lattice, but you cannot realize their exact chiral symmetries. If you could realize the exact chiral symmetries, then if you know how to gauge them, then you could do the rest. But we don't know how to realize the exact chiral symmetries of free massless fermions in 4D. And we put on a lattice, there's a doubling problem, but even with the doubling problem, we cannot do that. But I'm going to talk more about it in the next slide. So having said that's the definition of chiral gauge theory, I should say that in these theories, it could be that the IR theory have some emergent parity symmetry. Okay, and more drastically, it could be that even the UV theory might have a hidden parity symmetry and be non-chiral. So in these 3 lines is kind of a practical definition of chiral gauge theory. That's what it makes it difficult to put it on the lattice. But more invariantly, such theories might not be chiral because they might have some hidden parity symmetry. But this hidden parity symmetry might not help you to put it on the lattice. So that's why I'm going to use this definition of chiral gauge theories. But there will be more on these points at the end of the talk. Any questions so far? Okay. So let me tell you a little bit about the Nielsen-Ninomiya theorem and how I'm gonna avoid it. So what Nielsen-Ninomiya theorem, no-go theorem tells us, so in short, it tells us that there is no discretization of the Dirac operator such that it satisfies this 4 nice property. There is no discretization of the Dirac operator that is local in the sense that the Dirac operator is continuous in the momentum, that it realizes free fermion in the sense that for a small momentum, it looks like just the Dirac operator. There is no doublers in the sense that the only zeros at p equals 0, and it has an exact chiral symmetry. So that's some theorem about basically free fermions and discretization of Dirac operators. However, our strategy is to use duality, or in particular bosonization, and because of that, so we are not really trying to directly discretize the Dirac operators on the lattice, because our formulation of lattice chiral gauge theory is going to be in terms of bosons, in terms of fermions. And so in our lattice model, there is no notion of Dirac operator that we started with. And because of that, the Nielsen-Ninomiya theorem is just not applicable to our setup, because our setup is not fermionic degrees of freedom. We are going to use duality and bosonization. And so basically that's how we evade the Nielsen-Ninomiya theorem. We're going to construct some lattice model that, its low energy phase or continuum limit is a chiral gauge theory. So let me say a little bit more precisely what is our strategy. So it consists of 2 steps. the first step is to realize exact anomalous chiral symmetries on the lattice. And this is done by this technology of modified VLAN, formulation of compact boson, which has been discussed in many papers starting from 90s and more recently starting from 2019 and up to now. There are many, many papers. This is just a small list of the papers on this modified VLAN. So that theory allows you to have an exact chiral symmetries on the lattice. And the second important step is to how do anomaly cancellation, basically how to gauge anomaly-free yet non-on-site symmetries on the lattice. And there was, I discussed in this paper, a general strategy of how to gauge anomaly-free non-on-site symmetries, which I'm going to apply that systematic method here to actually gauge some anomaly-free combination of chiral symmetry. And then we would have some chiral lattice gauge theory. So that's the strategy. Any question? Okay. So let me
Sorry, I have a question.
yes,
So
yeah.
the second line, you say gauging normally free combinations. Can you explain? Why do you need to gauging?
So I mean, so let's say the big goal is to put something like a standard model on the lattice. So what's the property of standard model? You know, we have a bunch of left moving, right moving fermions, but they are coupled to the SUN gauge group or U1 gauge group in a chiral way, but there is anomaly cancellation. And so we want to have a chiral gauge theory. So here I will find, we will discuss some toy models that the U1 gauge field coupled differently to the left moving and right moving fermions, but yet the such that I have a chiral lattice gauge theory. And chiral lattice gauge theory is a toy model in 2D. It's a toy model for the standard model in 4 dimension.
I see. Thank you.
All right, sure. Thanks for the question.
Sorry, Sahand, did you already answer my previous question?
So, I try to explain like the difficulties. I said that one main difficulty is just how to realize exact chiral symmetries on the lattice.
Yeah, I was asking about the other difficulties. I was asking what you think are the other difficulties
Okay.
besides the anomaly-free chiral symmetry. For example, the gauge field may have some topological configurations, and if you put it on a lattice, the topology of the configuration may be ill-defined because of the discreteness of the lattice, and maybe there may be something else.
Okay, I mean, it could be that if you want to, for example, put the theta angle on the lattice, we don't know how to do it. But for the standard model without the theta parameters, I don't recall any other immediate difficulty.
Yeah,
Or I think
go
maybe
ahead.
they are not as important as this difficulty. I don't know anything.
But
Don't know.
then why do you not want to put the theta parameter into the standard model?
I mean, I don't know how to put theta angle. I mean, if you want to also put theta angle, that's also an interesting question. But I think the problem that we are facing that we don't know how to realize chiral symmetry is a more important one, is a more serious one. So we better first solve this one than the other ones.
Okay.
But we might not need to also put the theta angle on the lattice. It depends. But yeah, that's also an interesting question.
Thanks.
Yeah, thanks for the question. Okay. So let me be a little bit more specific. So the goal is to realize 1+1d anomaly U1 gauge theory. So we want to first start with n free Dirac fermions, meaning n left complex Y fermions and n right moving complex Y fermions. So we want to put this on the lattice and their exact chiral symmetry. So there is U1 to the n that acts on these fermions, and there is U1 to the n symmetry which acts on these right moving fermions. So we first realize this on the lattice, and then we want to gauge a single anomaly-free U1 symmetry where the left-moving chiral fermions have these charges and the right-moving have these integer charges. And so this doesn't have any gravitational anomaly because the number of left-moving fermions is equal to the number of right-moving fermions. So the left-moving central charge equals the right-moving central charge equals n. But it also wouldn't have any gauge anomaly if this anomaly cancellation formula is satisfied, meaning the sum of the square of the left moving charges is equal to sum of the square of right moving charges. And one popular option is the 3-4-5-0 model, where the left-moving fermions have charges 3 and 4, and the right-moving charges have 5 and 0. Okay, so that would be some specific model that we will discuss in detail. So that's the time model that we're gonna study today. That's just one prime example of chiral gauge theory. So then the outline of the talk, it would be, so first I will discuss this theory in a continuum completely and try to solve it. And then I will discuss the lattice formulation. And at the end, I will do the gauging and discuss two particular examples in detail and their spectrum. Okay, so let me start from a continuum theory. So as I said, one tool that is important in this talk is the bosonization, is the abelian bosonization, which in 1+1 dimension tells us that Dirac fermions is closely related to compact boson. So these two theories are very, very closely related, almost the same theories. So a Dirac fermions, a massless free Dirac fermions in 1+1d is related to the compact boson theory at radius r over 1 over root 2. So this is a Lagrangian for Dirac fermion, and this is a Lagrangian for compact boson, where phi is a scalar, is a compact scale, is a periodic scalar field, where phi is identified with phi plus 2 pi, and is at this radius. So this particular coefficient is important, that is 1 over 8 pi. So Dirac fermion has two U1 symmetry, U1 left times U1 right, and the compact boson theory also has two U1 symmetries. So one is the U1 momentum symmetry. So that's a U1 symmetry that shifts the scalar by constant. So you could shift phi by constant. That's the U1 momentum symmetry. But it also has a U1 winding symmetry that tells us that on the spatial circle, how much the phi field winds around the circle. And there is a nice dictionary between the two, is that the conserved charge for the U1 left symmetry is this linear combination of the momentum and winding symmetry. But that's part of the bosonization dictionary. And in particular, in the 3-4-5-0 model, the U1 symmetry that we want to gauge is associated with the following conserved charge, which in terms of the bosonic theories is correspond to these coefficients. So it's going to be 8, 4, minus 1, 2 models, because if we have to gauge this combination of momentum and winding.
Sorry, can I ask a question?
Yeah.
So I often see this U1M cross U1W, but I never see that, like, people, how do they write down the action of this U1W on this L boson? So can you explain it a little bit?
Good. So U1 winding doesn't act on phi. It acts on a dual field, which is phi tilde. So phi tilde is not, you cannot write it in a local way in terms of phi. So if you just look at this Lagrangian, so it acts on the vertex operator. So I cannot just write it in terms of phi. But fortunately, we're going to discuss some lattice model, and in the lattice model, there would be some local degrees of freedom where the winding symmetry acts on.
Oh, okay, I see.
So you
Thanks.
could only write the conserved charge. So you could write the conserved charge. I'm going to actually write the conserved charge, but the operator to charge under it, it's a bit non-local. It's a vertex operator.
But that means if you do the duality and then in the dual theory, you can write down U1W, but at that time you cannot write down U1M.
That's right. That's right. Yeah.
I see.
So that's T-duality. Yeah. Yeah. I will discuss T-duality a little bit.
Excuse me, I also have a question.
Yes, please.
Could you please explain why do we have this 1/2 in front of the QW?
Okay, so I could say that, let me first say that there is a little bit of asymmetry between momentum and winding, and that's related to T-duality. So when you do this bosonization, there are actually two choices. You could say Dirac fermions correspond to compact boson at radius 1 over root 2, or you could say at radius r, which is equals to root 2. And these two are related by T-duality, which exchanges momentum and winding. And so that's basically a choice you have to make here.
So if I change the radius, then this 1/2 also changes.
Yeah, so if you want to exactly land on Dirac fermion, the radius has to be either 1 over root 2 or root 2. And if you do root 2, you just have to change momentum and winding. You have to just swap them.
I see. Oh, I see. Thank you.
to discuss it more why it's exactly this form, I just have to do the Bosonization in detail. But yeah, just some part of the Bosonization. Thanks. Any other question? Okay, so this is just we start from a compact boson. It corresponds to a Dirac fermions, but now what we want to at the end of the day do is to have a different numbers of fermions. So we want to start with different numbers of compact boson. So let me say just say a few words about n copies of compact boson. So basically, you could consider n copies of compact boson. So for one compact boson, the Lagrangian is simple, but you could generally consider n compact boson, and the Lagrangian or the action is you can consider it to be more complicated. It has some more general moduli. In particular, so this is just the different ways of writing this kinetic term here. So if you write d mu phi, you could also write it in the differential form language. This is just a fancy way of writing the same formula. So it's going to be d phi wedge star d phi, but you could also consider compact boson at different radius and also consider some d phi 1 times d phi 2. At the end of the day, you have a general GIG symmetric matrix, which is called usually the metric. And you also have a so-called B field that it's an anti-symmetric real matrix, which gives you a coupling between d phi 1 and d phi 2, or like d phi I with d phi j for I different than j. So this is the general moduli. But and when you consider this n compact boson, you're going to find n momentum symmetries and n winding symmetry. And so this is basically the conserved charge associated to the momentum symmetry, which is going to shift each of the compact bosons by a constant. And this is going to be also the conserved charge associated to the winding symmetry. But that's basically the integral over d mu phi. So this generates these symmetries. And you could compute that there is actually a mixed 't Hooft anomaly between the momentum and winding symmetries. And it means that if you try to couple these symmetries to background gauge field, the action is not going to be gauge invariant. And then you could do an anomaly inflow to to make the theory gauge invariant by adding this bulk action. So you have to add this theory in the bulk, which is kind of a Chern-Simons term between the momentum and winding symmetry. So that's the anomaly theory.
Sahand,
Yes.
can you remind us again what's the constraints on GIJ and BIJ?
They are pretty much arbitrary. So Gij, it's a symmetric matrix. B is an anti-symmetric matrix. So maybe you just want the determinant to be non-zero. So that there is no.
Then how do you make sure that the charges of this momentum and the winding are integers?
Good. So the winding symmetry, the charge is always an integer because phi is 2 pi periodic.
Yeah.
And the same way here, again, because phi is 2 pi periodic. So this Jm is actually a conjugate variable to phi I. That's why it's integer valued. Because if you have a compact field, its conjugate variable is going to be integer valued. So that's a canonical momentum basically to phi I.
Oh, so this doesn't, even if I rescale G and B, it doesn't matter.
Yeah. So the way I read it, these are already conserved. They are already, quantized for any GI.
Okay, thanks.
Yeah, thanks for the question. And this anomaly is also unaffected. So I only wrote the most general thing because at some intermediate step, I'm going to apply T-duality, and T-duality will introduce this G and B. But my initial starting point is that B equals 0 and Gij is just a delta function because I just have n-decoupled fermions or n-decoupled bosons. Okay, so then looking at this anomaly polynomial, this anomaly theory, we could also discuss anomaly cancellation. So basically, let's consider a U1 symmetry generated by this combination of charges. And if we want to find the anomaly of this symmetry, we just basically have to substitute nm for momentum A for the background gauge field for the momentum symmetry, And for the background gauge field for the winding symmetry, we want to set it to be NW times A, where A is the background gauge field for this single U1 symmetry that you want to gauge. And so if you do this substitution, you will find the anomaly polynomial is just the usual Chern-Simons theory times this combination. So then you will find that the anomaly cancels if and only if the dot product of the momentum and winding symmetries vanishes. So remember that in the fermionic language, the anomaly cancellation was a different formula, which was the sum of the square of the left moving charges equals to the sum of the square of right moving charges. But because of this dictionary between momentum unwinding and left and right, the anomaly cancellation formula is slightly different. It's just the dot product of the momentum unwinding symmetry. So in particular, this combination of charges, which I told you, this 8, 4, minus 1, 2, satisfy this anomaly cancellation formula. Okay, so another trick which is useful, as I said, in some intermediate step is the T-duality. So T-duality is a statement that the compact boson theory at radius r is exactly equal to the compact boson at radius 1 over r. And so the way this T-duality works is that, so if you have a field phi, so phi tilde is defined by this equation. So you want the hot star of d phi to be d phi tilde, and vice versa, that d phi to be star of d phi tilde. So, the way I wrote it here is local, but if you want to get rid of d on the right-hand side, then that's why phi tilde is a non-local variable of phi. Anyway, so this T-duality exchanges phi with phi tilde and also exchanges momentum with winding symmetries. That answers some of the question which was asked earlier. Anyway, so this is T-duality for a one compact boson, but if you have n compact boson, the T-duality group is more interesting. So it's this large group. So it's the orthogonal group On, comma n with integer coefficient. And so this big group is generated by three sets of T-duality transformation. One set is just T-dualities of individual boson. The other one is just basically a coordinate transformation in the target space. It's basically a coordinate transformation on different phis. So if you have phi 1, phi 2, phi 3, you could view them as some coordinates, and you could do some GLNZ coordinate transformation, but with integer coefficient. And you have to do them with integer coefficient because these phi i's are periodic, are 2 pi periodic. So you cannot do arbitrary transformation. It has to be with integer coefficient. And finally, the last T-duality is the integer shift of the B field. So this B field, which is here, if you shift it by 2 pi, the resulting thing actually doesn't change the theory. It's a total derivative, but it's also 2 pi, so it's going to be trivial. Okay, and if you have such a general T-duality, it's going to act on the momentum unwinding charges as follows. So if you look at the vector of charges, it will transform under T-duality by basically a multiplication by this matrix O. Okay, so this is some exact duality which is derived many years ago. So it will be useful to solve the theory. So we're gonna solve this chiral gauge theory using T-duality. What's the strategy? So let's say we have n free fermions. We first bosonize them to n compact boson, and we want to gauge a single U1 symmetry. So the first strategy to solve the theory is to first perform a T-duality transformation that makes the vector of charges completely non-local. Sorry, non-chiral. So you want to find a matrix O that when it acts on the momentum and winding charges, you just get a single winding charge. So you just get the vector which has 0, 0, 0, a single 1, and all the other entries are 0. And there would be some GCD factor which is left over. So what it means is that we take this theory, we perform this T-duality, but after doing this T-duality in this new frame, the gauge charge is non-chiral, and it's only going to be coupled to single bosons. We could take that boson to be phi 1, the way I choose it here. And this matrix always exists. This is a math statement. And then the chirality is going to be hidden in just the moduli, the remaining boson. So after this to do T-duality, this is going to be our action. So we're going to introduce some G prime and B prime, but the gauge field only going to couple to phi 1. But this theory is going to become exactly solvable the same way that we solved the Schwinger model. So you could basically integrate out A, and once you integrate out A, it will do two things. First, it would make phi 1 non-compact, and second, the kinetic term for the gauge field is going to give us a mass term for phi 1. So phi 1 is going to be a non-compact massive boson, also known as the Schwinger boson. So at the end of the day, the theory has a very simple solution. So the theory factorizes as a non-compact boson, this phi 1 guy, decoupled with n-1 compact boson. These are the remaining boson, and they might have a non-trivial moduli. Maybe they might have non-trivial G prime and B prime. And there might be also a leftover Z gauge theory, which arises from this GCD. So this is the complete solution in the continuum. And we will see that all of this structure persists on the lattice. And that tells us that this method actually works on the lattice because we land on the same answer. Any question about this solution?
Just to make sure about the notation, here the G prime and the B prime are obtained from the T-duality starting from n decoupled boson.
Exactly.
In the case of n decoupled bosons, in that case, G is just some delta Ij and B is 0.
Exactly.
Okay,
Yes,
okay.
yes. Yes, thanks. Yeah. Good. So now let's start with the lattice model. So let me first start from the modified Villen formulation of compact boson. So let's take the compact boson and we want to put it on the lattice while preserving the exact chiral symmetry. So the idea is to first start from a non-compact boson theory. So consider a chain with L sides, a periodic chain of L sides, where at each side we have a single particle. So we have, let's say, we have a non-compact boson at each side. So we have a boson phi j and pj's canonical conjugate momentum with this canonical commutation relation. So the first term is going to be basically pj is like a d0 phi. So it's just basically d0 phi. And then the second term is just a discretization of the time derivative. So it's just the spatial derivative square. So this is literally the Hamiltonian of a non-compact boson. Okay, but this is non-compact. So the idea is that to make it compact, instead of starting from a rotor or a compact field, we want to start from a non-compact boson, and then we want to gauge the shift symmetry of phi to make it compact. So if you look at this Hamiltonian, it has a symmetry. You could shift phi by any constant. In particular, you could shift by any integer. So if you consider the symmetry that shifts phi by 2 pi r times any integer, it's a symmetry, and we want to gauge that symmetry to make it compact. So how do we gauge this symmetry? So it's a standard procedure. We want to introduce gauge fields on the link. So we introduce this integer valued gauge field p tilde on the link jj plus 1. And the first thing we do, we make the derivative into a covariant derivative. Okay. And then this gauge field also gonna has its own conjugate momentum phi tilde. And of course, we also have to impose Gauss law, which implements the gauge transformation. So the gauge transformation tells us that phi has to be shifted by phi plus 2 pi an integer n. And the gauge field p tilde is going to be transformed by the divergence of the gauge field n. Sorry, the gauge parameter n by delta n. And so this is basically the Gauss law at site j that implement this gauge transformation. And the fact that p tilde is integer valued, you could just impose it by this equation that e to the 2 pi I p tilde is 1. And because of this condition, phi tilde is not gauge invariant, means that phi tilde, which is conjugate to p tilde, is actually circle valued, meaning that phi tilde is periodic. So you could shift it by any 2 pi. Okay. So this is the model. 1 bosons per site. This is the Hamiltonian, and it satisfies these two kind of a local kind of Gauss type constraints. Okay, any question about terminology, this lattice model? Good. So the claim is that this exactly gives us the compact boson on the lattice and also exact chiral symmetry. So what are the symmetries of this model? So the first symmetry, it's a momentum symmetry which shifts phi by any constant. So basically, if you look at this Hamiltonian, it has a symmetry of shifting phi by a constant. But it also has, so that's the momentum symmetry, but it also has a winding symmetry of shifting phi tilde by a constant because phi tilde just doesn't appear in the Hamiltonian. And indeed, these two symmetries are generated by these conserved charges. So the momentum symmetry is given by the sum over Pj, and the winding symmetry is given by the sum over P tildes. But I wrote this combination instead of P tilde because this gives us the fact that this charge is manifestly gauge invariant. So the second term actually doesn't matter on a periodic chain once you sum over all J, but I wrote it here because this combination is gauge invariant. But the P tilde itself is not gauge invariant because P tilde doesn't commute with this constraint.
So do you mean even if I don't have the second term after the summation over J, this quantity is still gauge invariant?
That's right. So the sum is always gauge invariant, but the local terms might not be gauge invariant. I just wrote it this way so that it manifests the gauge invariance.
Okay.
So both are gauge invariant, but we want to also we want them to generate a U1 symmetry. So we want these conserved charges to be quantized. And you could see they are quantized by writing it in a different way. For example, this quantity is not quantized, but if you forget about the second term, P tilde is quantized. So if you write Q winding as a sum over P tilde, that would manifest the fact it's quantization. And similarly, you could add this term to P, and this combination in the exponent is integer. That would also tell you that why the momentum symmetry is quantized. Anyway, you could show that these are both gauge invariant and quantized. And how do we see the anomaly? So one way to see the anomaly is from the Schwinger term. So let's take the local charges, Pj, and the local winding charge, P tilde, and let's look at the commutation relation. So the commutation relation is the difference between two discrete delta function. And this is indeed the discretization of this Schwinger term in the continuum. So the way that you discover this anomaly, sometimes known as Schwinger anomaly, is to look at the commutation relation between the equal time of the conserved currents. And their commutation relation, it's a derivative of the delta function. And this is just its lattice discretization. So that's one way to see the anomaly. There are more systematic ways to see the anomaly, but in the lack of time, I will not explain it. And I should say this anomaly here is different from chiral anomalies of the model discovered in this paper and many other papers on the name of Onsager algebra. So those chiral anomalies are not really correspond to U1 symmetries because some of the charges are not quantized. But here is different because it's actually a U1 momentum times a U1 winding symmetry. So in that sense, it's different from these papers.
Sahand, do you mean
Yes.
the symmetries in the other papers are not U1 but are?
Yes, some of it is not U. Yes, yeah. So the momentum symmetry by itself is U1. The winding is U1, but the two charges don't commute with each other. So if you try to take the sum of the charges, it's going to be R. It's not going to be quantized anymore.
Thank you.
Sure, thanks for the question. But in this case, QM and Q winding, they completely commute with each other. So it's U1 times U1. Okay, another fact, as I said, which will be important is that this model has the exact T-duality. And the T-duality basically corresponds to changing phi with phi tilde. But because phi tilde lives on the link, we have to pick a direction. And here I've picked a direction of shifting everything to the right. So T-duality shifts the things on the side to the link to the right of it, and shifts the things from on the link to the side to the right of it. And if you look at this transformation and you apply it, you could see that it indeed generates T-duality in the sense that the modified Villain Hamiltonian at radius r after this unitary transformation becomes the modified Villain Hamiltonian at radius 1 over r. Moreover, this T-duality transformation is gauge invariant because it sends the Gauss constraint at site j to the Gauss constraint at link to the right of it, and send this Gauss constraint to the site to the right of it. So it's a gauge invariant unitary transformation which implements T-duality. And indeed, as expected, it exchanges the momentum with winding symmetry, and it also acts as a half translation. So if you do tau squared, you get just ordinary lattice translation by one side. So that's a nice feature which is different from the continuum.
Sahand,
Yes.
question about this phenomenon that T squared is translation. Is there any general underlying principle that requires this?
That's a good question. I don't know.
It appears in many contexts.
Yeah, that's right. It's also in the non-invertible symmetry on the lattice, which is absent in the continuum.
Yeah.
Yeah, it's a curious thing. I don't know if it's general or not.
Thanks.
Yeah, I don't know. Nice observation. Okay, so now I discussed modified villain. Let's go to the chiral gauge theory. So we start with n copies of modified villain. So we have basically this superscript I runs from 1 to n. And then we have n constraint per each side, and we have n constraint per each link. And we want to gauge a U1 symmetry. So we take this combination of momentum and winding symmetries where the anomaly cancels, and we're going to gauge them based on the general method described here. So I'm not going to tell you how I derive it from the general method. I'm just going to tell you the final answer. This is the final answer if you try to gauge them. So the first step to gauge the symmetry is to couple the theory to background gauge field. But coupling the theory to background gauge field corresponds to insertion of defect for this symmetry. So the way we do it is that we want to insert defect for this symmetry, and the insertion of defect is done by implementing the symmetry on half of the space. And if you follow this route, you will find this is the way that the gauge field will couple to the theory. So there are two ways to couple the theory to background gauge field. One is to couple it through the Hamiltonian, but for convenience here, I chose to couple it through the modification of Gauss law, because insertion of defect can be thought as the modification of Gauss law. So and that's the answer. To couple the theory to a background gauge field, you have to modify the Gauss law at site like this, and modify the Gauss law at link like that. So this n winding is just the charges, this n winding and n momentum. And AJ is some circle valued U1 gauge field. So that's the first thing. The second thing, you want to make the gauge field dynamical. So to do that, first we want to introduce the conjugate variable to the gauge field, the so-called electric field EJ, which satisfy this commutation relation, and then impose Gauss law constraint, which is the standard Gauss law constraint. It tells us that the local charge corresponds to the divergence of the electric field, and that's the lattice version of it. And because the gauge field is circle valued, its conjugate momentum electric field is quantized. So electric field is integer valued, meaning e to the 2 pi I EJ equals 1. And we also have to add a kinetic term for the gauge field, which is roughly sum over EJ squared, but we could also introduce a theta parameter, and there's also this extra term that we have to add for gauge invariance. So this awkward term might not be familiar with people. It might be strange for people that do usual lattice gauge theories. And this is there because I chose to couple the gauge field to the Gauss law instead of the Hamiltonian. In the next slide, I'm going to use a different alternative presentation. So basically, this is the answer. And let me just flash it. If you're uncomfortable, you could apply a unitary transformation whose explicit formula is given by this to change the theory such that the gauge field coupled through the Hamiltonian. So in this alternative presentation, you have to make PJ into a covariant derivative, basically time covariant derivative, and you make also this derivative into a covariant derivative by introducing this AJ plus 1. And then this awkward term is gone, but the price you pay is that now the electric field is not quantized. So this might be more familiar to people. But anyway, I'm going to use this presentation for my chiral gauge theories. Okay, so this is a bit complicated. It's hard to absorb. So just to convince you that this is the correct answer, I'm going to do 2 concrete examples and solve this model exactly for you on the lattice. Any question? Okay, so the first example I'm going to do is just the massless Schwinger model. So basically, you want to start with one compact boson and its gauge is winding symmetry. So there is a single boson phi j and pi j, and I just follow what I said before. I have to modify this Gauss law. I just put e to the iaj, and then this is just the Gauss law for the U1 gauging, and this is the quantization of electric field. So to solve this, we have to perform a unitary transformation. So if you apply this unitary transformation given by this, then this further simplified. Because after doing this gauge transformation, this Gauss law simply becomes P tilde equals 0. So then P tilde is completely gone because P tilde is 0, so you could just drop it. Moreover, this term is gone, so it means the gauge field AJ and EJ completely decouples from your Hamiltonian. So you are left with a non-compact boson because pi j and phi j and pi pj don't satisfy any Gauss constraint. So they are actually non-compact, and this is their Hamiltonian. So if you see, there is a spatial derivative, there's a time derivative, and now there is a mass term for the scalar field. So basically, this Hamiltonian describes a non-compact boson of mass m equals e over root pi, which exactly coincides with the solution of the Schwinger model in the continuum, which was solved 60 years ago. So this is just a check that this strategy was correct, because the solution we get is exactly matches with the continuum. So another test we want to do, we want to just do this famous 3450 model. So as I said, in the bosonic language, 3450 model corresponds to this combination of charges, 8, 4, minus 1, 2. And if you do the procedure I explained before, this is the Hamiltonian you get. So there are two flavors of bosons, and there are these many constraints. So this looks a little bit complicated, but as I said, the strategy to simplify it is to apply a T-duality transformation so that it makes the charge which is being gauged completely non-local. And then we could try to decouple the gauge field completely from the system. And it turns out that this T-duality exists. There is an explicit formula on the lattice. So I'm going to just flash you the formula. So this is the T-duality in this case. So T-dualities correspond to this particular matrix, which changes the vector of charges to be non-chiral. And this is the explicit lattice realization. So you could check that there is a unitary transformation that does that. Anyway, after you apply this unitary transformation and also this extra unitary transformation, you get this new Hamiltonian. So, okay, so QJ here is, I forgot to write it down, is basically the second Gauss law on site. So it's P plus delta phi tilde. So you still have a Gauss law for the second boson, but the Gauss law for the first boson is completely gone because P1 tilde is 0, and the gauge field also completely decouples from your Hamiltonian. So now this Hamiltonian is very simple. So it's the second boson is still compact, but the first boson now is non-compact. But I should also say that this is a bosonic theory, but we could also make this theory fermionic. So to fermionize the model, we want to do a fermionic gauging of the Z2 subgroup of the second winding symmetry. So there is a systematic procedure to do bosonization and fermionization on the lattice. For example, there is a general procedure, and if you apply it, let's say, to Majorana chain, you get the Ising model, and from the Ising model, you get the Majorana chain, which in this particular case is going to reduce to the Jordan-Wigner transformation. But there is a more general way to do bosonization beyond the Jordan-Wigner transformation, and that's correspond to gauging of Z2 symmetry. And if you follow that general procedure, which in this paper I explained in Appendix A, is that it amounts to modify the two Gauss law that you get here. So if you take these two Gauss law, you could modify it in the following way. So you could introduce two Majorana fermion per each site, psi j and psi tilde j, and you could modify the Gauss law in the following way. So the first modification, this one, correspond to coupling the theory to fermionic Z2 gauge field. So that's how the fermions actually couple the theory. And the second modification here, it's a Z2, it's a Gauss law for the gauging Z2. And if you square this relation, you get back to the original Gauss law. So the second condition is the original Gauss law plus the Gauss law for the gauging Z2. So this gives you the new Gauss law, and this gives you the coupling of the theory to this Z2 gauge field. And the resulting theory is a local fermionic theory, whose degrees of freedom is both bosons and fermions. And so putting everything together, this is the theory that we end up. So it consists of two bosons, phi1 and phi2, two Majorana fermions per site, and one bosons per link. And these are the constraints. This is the Hamiltonian. This is quadratic. Actually, you could completely diagonalize theory and solve it. And so because of this T-duality, we could solve this theory. And if you find a spectrum, you find this simple answer. You will find that the spectrum corresponds to a massless Dirac fermions completely decoupled from a Schwinger boson of mass m, which is equal to 5e times e over root pi. So that's which is going to appear in this work in progress soon. So what this implies, it means that the 3450 model actually has a hidden reflection symmetry, which is not manifest in the original fermionic degrees of freedom. So the theory is actually non-chiral, even though it's usually advertised as a toy model for a chiral gauge theory in 1+1 dimension. If we don't introduce any mass term, this theory is actually secretly non-chiral.
Sorry, just to make sure. This theory, when you say the spectrum is massless Dirac fermion and the Schwinger boson, you mean the entire spectrum, not just the knowledge spectrum, right?
Exactly. Yeah. So this is exactly true in the UV, and also in the lattice model that we construct is exactly true at yeah.
I see.
This factorization is exact.
So the reflection symmetry is also exact.
It's also exact, but yeah, so in the fermionic degrees of freedom acts in a non-local way, but in the lattice model, you could just write it down. It just acts locally. It's just hard to see, but with this T-duality trick, you could see it.
I see. Thank you.
Yeah, thanks for the question. Yeah, it's a bit surprising. Actually, it's not surprising from a continuum point of view, but from a lattice, it's surprising. Anyway, it's not surprising if you know about T-duality. Right, let me put it this way. So to get a chiral gauge theory, we actually need, you could get it, but we need more than 2 Dirac fermions. So we have to start from at least 3 Dirac fermions. And we can also make this theory more interesting, and we could break its exact solvability by introducing mass term for the fermions. For example, we could study even the two-flavor massive Schwinger boson model has a very rich phase diagram, which was studied in this nice paper. So let me summarize. So we constructed exactly solvable chiral lattice gauge theory for a billion gauge theories in 1+1 dimension. And the two techniques by the exact realization of chiral symmetries and by gauging anomaly-free combination of them. So modified Villain realizes not only the symmetries, but realizes the moduli of all compact bosons. So from modified Villain, you could realize arbitrary G and B field, these Gij and Bij. But not only that, you could also realize the full T-duality on the lattice. And that was helpful for us to solve the model. And actually, some of this strategy can be applied in 4 dimensions, even though there is no T-duality. So it turns out that in 4 dimensions, there is a lattice realization of exact U1 vector times U1 axial chiral symmetries and its anomalies, which was discussed in this nice paper. And we also described a concrete lattice Hamiltonian model that realizes these symmetries. So some open question is to generalize it and find the non-abelian gauge groups. For example, can we have non-abelian chiral gauge theories on the lattice? And the second thing is about 4D. Can we realize, so these 2 papers here only realizes the pure U1 anomalies. Is there a way to realize chiral symmetries in 4D with U1 gravitational anomaly? But I didn't have time to talk about this, but this is something that we currently don't know how to do, and we have to solve this if we want to ever put a standard model on the lattice. And with that, let me thank you for attention.
Okay, thank you, Sahand, for the very nice talk.
Yes.
Any further questions? I have a question.
Yeah.
I think although, of course, I'm not able to catch all the technical details, and they are not during the talk, but I think the overall structure of the work is very clear and the presentation is very clear. What I want to ask is, what do you think is the most crucial insight behind this work and the one that you are about to post?
You
It's
mean
a subjective question.
what's the new ingredient? What's the question again?
What's the most crucial ingredient?
What's the most crucial ingredient? I
Or
think
sorry, what's the most crucial insight?
insight.
It's a subjective question.
So I think that there's a combination of techniques that we are using here. Like there are three. I could say there are three ingredients. I don't know which one is the most important one, but there are three ingredients. One is the fact that modified VLAN is just does too much. It allows you to realize exact color symmetries on the lattice. That's one of the big ones, big important ones, is to how to just realize exact color symmetries on the lattice. U1 times U1, and modified VLAN allows you to do that. So that's one important ingredient. Another one to me is just to how to gauge a non-on-site symmetries.
Which you
And
developed before.
yeah, and in this case you could see it, but as you say, it's complicated. But I think with the method that I had before is more systematic. And I should say that that's exactly how my paper is different from this paper by Ryan Torngren, John Preskill, and Lukasz Witkowski. Because the way that they gauge the symmetry is that they don't have a systematic way to gauge the symmetry. So what they do is that they first try to make the symmetry on site and then gauge the symmetry. So the way that they make the symmetry is on site is by this symmetry disentangler method, which is related to our work with Wilbur. So with Wilbur, we study in 1+1d how to make any non-on-site symmetry on site if it's anomaly free. And actually, the way we did this symmetry entangler was inspired by the gauging method. So I would say they are both boils down to the gauging method, because the gauging method was crucial for the symmetry disentangler, which this paper used.
Mm-hmm.
So I think the other one is the gauging non-on-site symmetries. And another magic, which might not be important for the final goal of putting standard model on the lattice, is this T-duality that the modified VLAN allows you to do that. But that's just for the exact solvability of the model. We don't expect it to hold for 4 dimension.
Mm-hmm.
Yeah, so
Okay.
these are the ones.
Thank you. Any other questions?
Yeah.
Yes. Could you please again explain how do we get a chiral theory by increasing the number of fermions, if you said that?
Sure. So you see, there is this factorization that I explained here. So I said that after doing T-duality, the gauge field only couples to one of the bosons and basically make that boson non-compact and massive. So you start from n boson. After gauging, you strip up one of them and you make it non-compact. And then you are left with n minus compact boson. But if n equals 2, you are left with one compact boson, and one compact boson is always non-chiral. But if n at least is 3 for 2 compact boson, this B prime field could make it non-chiral, because two compact boson with arbitrary G prime and B prime could be chiral. Yeah.
I see. Thank you very much.
Yeah, excellent question.
Okay, any other questions? Okay, if not, I will represent everyone to thank Sahand again for the very interesting talk. Thank you, Sahand.
Thank you.
Yeah, okay, bye.
Bye. Yeah, thank you very much. Bye.